So we are discussing the complexation of actinides, and subsequently we also discussed about the extraction of actinides, which has relevance in the nuclear fuel cycle, specifically for the reprocessing of spent nuclear fuel. I will give some more details on this application of complexation and extraction of actinides in today's lecture. Now this is for the extraction of tetra as well as hexavalent actinide ions. Hexavalent means, as I have already mentioned, the ionic species is ANO2 2+, where AN stands for the actinide element. That is for uranyl ion, UO2 2+, and like that for neptunium and plutonium. And the profiles I have shown in this slide are the comparative extraction of +4 and +6 actinides by TBP. Now TBP is 30% TBP here. The solution made in aliphatic diluent like kerosene or dodecane. And the left side figure gives the extraction of tetravalent actinides by 30% TBP. The extraction equilibrium for this is given here. First equation gives the extraction equilibrium, where the tetravalent metal ion in the aqueous phase is forming a complex with 4 nitrates again in the aqueous phase and 2 TBP present in the organic phase, and resulting in a complex of the type MnO3 4 times 2 TBP, which is favorably partitioned into the organic phase. So the left side profile shows that of the tetravalent actinide ions. You can see that the extraction of plutonium-4 is increasing with increasing nitric acid concentration. You see that this extraction is going up, and beyond around 6 molar nitric acid, then it falls. So that is because of 2 factors. As I have already mentioned, in this extraction equilibrium, with increasing nitric acid concentration, the nitrate ion concentration is increasing. Therefore, the formation of this species, that is MnO3 4 times 2 TBP, this species is increasing with increasing nitrate concentration. That is, with increasing the nitric acid molarity, this extraction should increase. However, beyond around 6 molar nitric acid, this extraction of this tetravalent ion, here in this case plutonium 4+ ion extraction, is decreasing. That is because of 2 factors. Number 1 is that TBP is forming a complex with nitric acid, that is TBP HNO3. This type of complexes are formed. This can be 1 HNO3, depending on the higher concentration, it can be 2 HNO3, like that. These adult species are formed. That reduces the effective concentration of TBP in the organic phase. That is why the extraction of plutonium 4+ is decreasing. And the second reason is that plutonium at higher nitric acid concentration forms anionic species. This is like PuNO3 6 times 2-. So this type of species are formed at higher nitric acid concentration, maybe something like 6 to 7 molar nitric acid or beyond. So that is the second reason why the plutonium extraction is decreasing. Similar behavior is seen for neptunium 4+ ion as well. On the other hand, is thorium extraction is significantly lower, as you see here, and at a higher nitric acid concentration, the thorium extraction is increasing. That is because of some salting out effect. Now coming to the hexavalent actinide ions like uranyl, neptunium, and plutonyl ions, the extraction equilibrium is given by the second equation here. That is, the actinyl ion in the aqueous phase binds with the 2 nitrate ions present in the aqueous phase, and 2 TBP present in the organic phase to give this extracted species. You can see this 2 species for the tetravalent as well as the hexavalent ions. You find that the number of TBP molecules are same for both. So that means the organophilicity of this extracted complex due to the presence of TBP is same for the tetravalent as well as the hexavalent metal ions. On the other hand, for the tetravalent metal ion, we have 4 nitrates. So the nitrate ions are more favorably partitioned into the aqueous phase. So that is the reason why this MnO3 4,2 TBP species is partitioned less towards the organic phase compared to the MO2 NO3 twice 2 TBP species. And that is the reason why uranium 6 extraction is higher than that of plutonium 4 extraction from nitric acid medium using TBP. Now this extraction of these hexavalent metal ions are giving the right side figure where you find the uranium 6 extraction is higher than that of neptunium 6, which is in turn higher than that of plutonium 6. Now the relative trend of this extraction of the actinide 4 and actinide 6 metal ions by 30% TBP from nitric acid medium is given here, where you find that the uranium 6 extracted higher than that of plutonium 4, which is extracted higher than neptunium 6, which is extracted higher than neptunium 4, which is extracted than plutonium 6, which in turn is extracted higher than thorium 4. So thorium 4 is least extracted out of these actinide ions. Now this has relevance in the Purex process, as I have already mentioned. I come to the advantages of the Purex process. It is a complete process because it has been used for the last several decades. The technology is very well known. TBP, which is used as the extractant in case of the Purex process, is cheap and easily available. So it actually helps in the economy of this process. And this degradation products of the TBP, which are monobutyl phosphoric acid and dibutyl phosphoric acid, they can be washed out easily using sodium carbonate solution. Decontamination factor of the fission products are large, that is greater than 99.9% of the fission products are separated during the Purex process. But there are some disadvantages of the Purex process. That is, the aqueous solubility of TBP is quite significant. That is 0.4 grams per liter of TBP is going to the aqueous phase. Then generation of solid waste. So finally, after this spent solvent, it has to be managed actually as a solid waste, which is the phosphates. And this TBP actually this fails the CHON principle. So this is a green extractant which should have carbon, hydrogen, oxygen and nitrogen. So TBP is not that type of extractant. It contains phosphorus. So it fails the CHON principle of the green extractants. And also this difficulty in plutonium loading when you go for the fast breeder reactor spent nuclear fuel. So in that case, plutonium concentration is much higher. So in that case, we find the third phase formation with this process. So for that, what are the alternatives? That we have to go for other processes, like which is called the Impurex process. That Impurex means it is improved Purex process. So now in case of the Impurex process, the extraction of uranium and plutonium is carried out at a higher temperature. So say around 60 degrees Celsius. So in that case, the plutonium extraction becomes higher and uranium extraction becomes lower. So in view of that, plutonium loading can be increased. There is another alternative is to go for the branched alkyl group phosphates. So that is like triisoamyl phosphate or TIAP, which has been tested in different laboratories to show that it is having much higher plutonium loading and third phase formation problem is less. And finally, there is this dialkyl amides like DHOA, that is a dihexyl octanamide. This has been found to be one of the most useful extractant in place of TBP. And for this, a lot of research has been carried out by the French researchers, and they have suggested DHOA to be one of the possible replacing extractants for TBP. I have shown here the profiles of TBP and DHOA in these two figures below. The first figure, the left side, gives that of TBP and DHOA for uranium extraction. The data given in the black line is the tracer data for TBP, and the green line is the tracer data with DHOA, and also the data is there with 50 grams per liter uranium loading. So there you can see that compared to TBP, this is the red line, the DHOA extraction data is somewhat inferior. But nevertheless, you can get reasonably good distribution ratio values, around 3 to 4 molar nitric acid, even with DHOA. This is a dihexyl octanamide. On the other hand, the plutonium extraction data is given in the right side figure, where very interesting observation has been made that the TBP and DHOA under 50 grams per liter uranium loading, the data is given as the red line and the blue line respectively, and you can see that beyond 2 molar nitric acid, the extraction by DHOA is better than that of TBP, and also less than 2 molar nitric acid, the extraction of TBP is better than that of DHOA. So this suggests that if you have higher plutonium loading, you can increase the nitric acid concentration and you can have higher extraction of plutonium-4, and at lower nitric acid concentration, plutonium D values become so less, shown here, that this plutonium can be stripped efficiently without using a reducing agent as in the Purex process. This is a big advantage of this dialkyl amide extractant DHOA for spent fuel reprocessing. Nevertheless, this has not been used, it's still in the testing stage. Now coming to the application and complexation of actinides. So for this, there are two more processes, is the DAPEX process and the AMEX process. These are the front-end processes where the uranium extraction is done from the leach leaker. The uranium from the ores, actually you can see that it is leached out using either acidic leaching or alkaline leaching. So again, using our complexation theory, whatever we have already studied in these lectures, uranium forms good complexes with sulfate as well as carbonate. So that is why dilute sulfuric acid or carbonate solutions are used for the leaching. Now this DAPEX process is actually dialkyl phosphoric acid extraction process. It is a short form is a DAPEX, and the extractant used is HDEHP. This is a phosphoric acid extractant as shown here. Structure is given here. This HDEHP actually in non-polar diluents, it forms a dimer as shown, the structure shown here, and then always while writing the extraction equilibrium, we write HDEHP twice. That means this is a dimeric form of HDSP. As shown in this extraction equilibrium here, UO2 2 plus 2 units of this dimer of HDSP is giving this extracted product here. That is the UO2 HDEHP dot DEHP. That means from here this hydrogen ion is replaced and then this is forming a chelate complex with 2 units of this dimer. So uranium is here and it forms complex like this, binding to these 2 oxygens. Now this extracted species can be stripped to give the uranium product by acid stripping as well as alkaline stripping. By alkaline stripping as shown here, you can use sodium carbonate and you get uranyl carbonate which has the product, and by acid stripping you can use different acids and you find this reaction here where you have this uranyl ion coming to the aqueous phase. There is another process in the front end where this sulfate leach leaker is actually used for the uranium extraction. That is the AMEX process where one tertiary amine is used, that is trioctylamine, and amine is better for the uranium uptake from sulfuric acid leach solution because uranyl ion forms an anionic complex in the sulfate medium, and that extraction equilibrium is given here. You see that this anionic complex of uranyl ion is actually forming complex by some sort of a ion pair type of extraction mechanism, and you see that R3NH plus is actually binding with UO2 SO4 3, 4 minus. And then this extracted species can lead to the uranium by a stripping mechanism, which is given below. You can have either this stripping mechanism, or by the carbonate method also you can have the stripping of to uranium. So that is how this uranium stripping is done. Now comparative extraction of this +4 and +6 actinides by trioctyl amine and xylene as the solvent system. I have summarized here for both tetravalent as well as hexavalent actinide ions. You can see here the left side figure gives the extraction profiles using 10% trioctyl amine in xylene, and you see that this plutonium 4 extraction is higher than that of neptunium, and then that of thorium are shown here. These extraction profiles are there shown here, and uranium 4 profile is not very clearly shown here. But in the right hand side figure, we show the uranium 6, neptunium 6 as well as plutonium 6 extraction profiles as a function of the nitric acid concentration. And you see that with increasing nitric acid concentration, the extraction increases and then subsequently it falls down. That is because of the competition between the nitrate ion with that of the anionic complexes of the actinide ions. So these actinyl ions, they form anionic complexes as I have mentioned. It's like PuO2. This can also form nitrate complex. This type of species it can form, and then with a increasing nitric acid concentration, you can find that this species is forming to a large extent, and then that is how it is getting extracted. And subsequently at higher nitric acid concentration, because of the competition with the nitrate ion, so it actually falls. Now this trend of this actinide ions or the actinyl ions with the amine extractants like trioctyl amine is given here. So where this tetravalent plutonium is extracted to a much larger extent than that of uranium tetravalent, and which is in turn larger than that of the neptunium 6, that is NpO2 2 plus ion, which is larger than the PuO2 2 plus ion, and which is larger than the uranyl ion, and finally the thorium 4 plus ion extraction is very, very less. Now the one thing which is very common in our nuclear fuel cycle, that we have to go for alternative fuel elements, that is the fissile element, that is uranium 233, which will be used in our future reactors by our AHWR process. That is why it is very important. And for that, this is the decay scheme which is shown here, how this thorium 232 is irradiated in the nuclear reactor, and to give the product, that is uranium 233, and also along with uranium 233 we have uranium 232, which has decay products which give hard gamma rays, and that is how this separation of uranium 233 is very, very important. And also from the bulk of thorium, this uranium 233 separation is required. This 233 uranium can be used in the reactors. So the extraction can be done by TBP, similar to the Purex process, and as mentioned in this case, uranyl ion is extracted by 2 nitrate and 2 TBP, giving this species UO2NO3 twice 2 TBP. Plutonium gives species PuNO3 4 2 TBP, and thorium 4 plus when it is there. So this extraction is not same as that of plutonium, but more number of TBP are required because thorium has lower ionic potential, so the complex formation is relatively lower compared to that of plutonium 4 plus. That is why more number of TBP molecules are required to form organophilic complex. That is how this type of species which are shown here, that is thorium nitrate X TBP, where X can be either 2 or 3 depending on the TBP concentration. Now there are two types of TBP thorax processes. One is called the thorax 1 process, where 5% TBP is used for the extraction of uranium from thorium, protactinium and the fission products. And there is another process called the thorax 2, where 40 to 55% TBP is used for the extraction of uranium and thorium from again Pluton, protactinium and the fission product. So the first process, that is the thorax 1, it is having much lower concentration of TBP, that is how thorium extraction is prevented, and only uranium is extracted. And for thorax 2 process, both uranium and thorium can be extracted. However, the separation factors which are obtained in case of this TBP based separation processes are relatively less. As shown in this figure, it is much less than 200, the separation factor, that is the distribution ratio of uranium divided by that of thorium. On the other hand, one of these dialkyl amides, which is a branched dialkyl amide, this structure is given here. This is termed as di-2-ethyl hexyl isobutyramide, or DIHEBA, di-2-ethyl hexyl isobutyramide. So this gives a very favorable separation factor for uranium 6 vis-a-vis that of thorium 4, and you get separation factor in excess of 3000 as shown here in this figure. So suggesting that this branched dialkyl amides can be used for the thorax process as well. Now we are discussing about the solvent extraction based separation of actinides. Now also there are these ion exchange resins, they are also used for the separation of actinides. So the separation again by different ion exchangers follows the same trend as we have seen in the case of the complexation of actinides with different ligands. Now as we know, in case of the ion exchange resins, we have one called a cation exchange resin, where we have strong acid cation exchange resin. So in that case, we have this sulfonate group which is there, which is actually replaced, and that is how we have this sulfonic acid group which is there, where the hydrogen ion is replaced by the cationic species of actinides. And also we have this anion exchange resin, where the anion of this resin which is there, like the chloride ion, is replaced by the anionic complex of the actinides. So the uptake by the cation exchangers, the cation exchange resin is given here. First is the tetravalent actinide ions which form strong complex, and it is uptake is definitely much larger than the other type of actinide ions. So it is followed by that of the trivalent actinide ions, followed by the actinyl ions plus 6, that is MO22 plus, which is higher than that of the actinide plus 2 metal ions, and finally that of the actinyl plus 5 metal ions. Now, based on this cation exchange resins, the separation of actinides has been attempted. We have already given one example where this DOX 50 cross 8 resin has been used for the intragroup separation of lanthanides and actinides, where this complexing agents like alpha hydroxy isobutyric acid has been used as the eluting agent. That is one of the application of this ion exchange resin. And also, as I have seen case of the ion exchange resins, the affinity difference between the cations is very large in case of the cation exchange resin, so the separation is relatively easy. On the other hand, the disadvantage is that many of these actinide ions can be absorbed onto the cation exchange resin to different extent, making it difficult for their separation, or the separation can be done by tuning the ligand property so that you have the element containing a selective ligand for a particular actinide ion that can bring down the metal ion from the loaded resin. So as some example I want to give for this organic ion exchange reagents, cation exchange reagents, I have already given this intragroup separation. Also, lanthanide actinide separation can be done, loading the lanthanide and actinide ions onto cationic ion exchange reagent and eluting by concentrated hydrochloric acid. Better results has been obtained to take ethanolic solution of this hydrochloric acid also, get better separation of these lanthanides and actinides. This is in addition to what I have already discussed, the intragroup separation, where this hydroxy carboxylates like alpha hydroxybutyric acid has been used. We also use inorganic cation exchange reagent like zirconium phosphate, which also take up the metal ions very efficiently. But in this case, the uptake is slightly different than what has been there for the organic cation exchange reagents. So for organic cation exchange reagents, which are mostly the gel type reagents, so in that case, the separation is done based on the hydrated radii of the metal ions. On the other hand, the inorganic ion exchange reagents like zirconium phosphate, the uptake is based on the naked ionic radii of the metal ion. The left side figure gives the uptake of actinide ions onto zirconium phosphate from nitric acid molarity. You can see from starting from 0.01 to 1 molar nitric acid concentration. And we have seen this americium 3, curium 3, californium 3, cerium 3, europium 3, cerium 4, and uranium 6 uptake by this inorganic ion exchange regime. And you see here that the uptake of the trivalent ions are relatively less compared to that of the actinyl ion. So that is, you see that this uranyl ion is preferred by the zirconium phosphate over the trivalent actinide ions like americium 3, curium 3, etc. This ion exchange reagent also has been used for the separation of actinides using anion exchange reagents. Now in that case, this actinide and lanthanide separation, I have mentioned previously the Tramex process, where we have used strong chlorine medium. Around 11 molar lithium chloride has been used, where the actinides form stronger complexes than that of the lanthanides, and the extraction has been done into an amine extractant, and that is how the separation of actinides are done from the lanthanides. Also, anion exchange reagent can be used for the selective uptake of uranium from hydrochloric acid medium, where uranium forms anionic species like UO2, Cl4, 2-, and many of these are rare plants where uranium also is one of the products. They use this method from hydrochloric acid medium. They try to recover uranyl ion by this anionic complex of uranyl ion. Plutonium also forms anionic complexes, and these also are separated by using anion exchange reagent. And this plutonium 4 is the species which forms, as I mentioned, PuNO3 6 2-. This type of anionic species are formed with plutonium 4 plus ion, and this purification of plutonium in our Purex process is finally done by taking plutonium 4 in 7.5 molar nitric acid and using anion exchange reagent like DOX1 cross 8 or 1 cross 4. I have given a profile of this plutonium uptake by anion exchange reagent from the nitrate medium. See that this cross-linking of the anion exchange reagent has a role. Increasing the cross-linking, the uptake of plutonium has decreased. They are given 3 different cross-linking, that 1%, 4%, and 8%. And you see that with 8% cross-linking, that is DOX1 cross 8 resin, the uptake of plutonium has been much lower than that of the 4% cross-linked resin, which is much lower than that of the 1% cross-linked anion exchange resin.